So let me recall. So first is chapter 3. So let me recall what we did yesterday. So we saw some basic properties of the Laplace transform. Laplace transform. So what were they? Can you name? Linearity, change of scale, okay, change of scale. So let me write down what it was. So L of C1F plus C2G, what was it? C1 capital Fs plus C2 GS, where capital F and capital G are Laplace transforms of small f and small g. What was change of scale? L of f of at is 1 by a f of s by a. So a greater than 0. This is important, yes? Change of scale, okay. The third thing, first shifting property. What was that? L of e to the at ft is f of s minus a is greater than a. Okay. Then comes second shifting property. What was that? L of t minus a. What is it? Sorry? Unit step function, yes, but I haven't talked about it. It is the unit step function. So this is a function gt which is made out of a ft. So what is gt? This is f of t minus a, t less greater than a, and 0 for t less than a. And for this, the Laplace transform is sorry, yes, f of s, right? So we will talk about unit step functions today, and in fact this gt can be written as ft minus a u t minus a, where u is the unit step function. So it looks something like this. So this is the step function. This is 1 for t positive and 0 in the negative part. So this is u t minus 0. This is 0. Okay. So we can shift anywhere we like. So suppose a is positive, and so we shift to the right. So at a, this is a, this is a. Now here is t equals 0. So it makes the function for t less than a vanish. When you multiply here, then gt will be 0 for t less than a, and it will be the same for t greater than a because it's just 1 in this part. Okay. Very good. This was the second shifty property. I will talk more about it. We will see the Laplace transform of the unit step function also. What else? Sorry? Derivative, na? Right. So, Laplace of derivative what was this? L of f prime of t is, what was it? SFS minus small f or capital F? Small f. Small f 0. Okay. And we saw that there is some subtlety involved here, that f prime t need not be of exponential order. If f is of exponential order and differentiable, then the Laplace transform exists, even though f prime may not be of exponential order. Okay? This part is clear? Okay. So, we can generalize this for n terms, and this is s square, s to the n f of s minus small f or capital F? Small f. What was it? Derivative, no? Sorry. Yeah. F of 0. Yes. And then it goes on, and in the end you get f of n minus 1. Yeah, where is the minus sign? I might have. Here?
The last one.
Okay. Is it minus 1 to the power minus n or something? Just minus. Okay. Thank you. Very good. So, we have done derivatives. So, today we will do multiplication by t, division by t, and also Laplace transforms of integrals. Okay. Okay. So let me start with division by t. Okay. So division. So which one? What's the number, 9 or something? Huh? 6. Okay. Laplace transform of function divided by t. So, suppose ft is of exponential type, okay, and fs is the Laplace transform of ft, then the Laplace transform of ft over t is what? Integral of s to infinity, not s, fu, because the I put s here. So this is g of s So the integral, the variable inside the integral should be different from s. So it's the integral of f u du. Are there any conditions? Yes. What should exist? Yes. Provided limit of ft over t goes to 0 or infinity. So if t goes to infinity, let's think about it. Okay. Yes, it should be 0. If t goes to infinity, what will it be? No, just this limit, well, what will it be? Should be 0, right? Why? Yeah, so f of t may not be bounded, but it is of exponential type, right? So the limit, if you take the infinity, then you can bound it by is it true or not? Because then you will have the limit t tends to infinity m e to the alpha t over t. There is a problem, okay? So it may not be 0. If you're right, if you are having f to be bounded, then it's true. So then this thing goes away, okay? Then it will be 0. Otherwise, it may not be 0. Can you give me a function which is of exponential order, whose limit ft over t as t tends to infinity is unbounded, is not convergent? Cos of? That's also true. You can just take any degree t to the n, where n is greater than 1, and you will have something. So we don't want the limit at infinity. We actually want the limit at 0, provided this limit exists. So let's try to prove this. Okay, proof. So let's start by just writing out the formula. G of s is equal to 0 to infinity f of t over t exponential minus st dt. Right? Now, how can we express this in terms of the Laplace transform of f? Any ideas? Yes? Right. So what's the derivative? The s derivative, yes? You want the s derivative. So exponential of e to the minus st, this is minus t e to the minus st. So when you are integrating e to the minus st, you will get a t in the denominator, okay? So we will use that trick. So this is integral 0 to infinity ft integral e to the minus s, not s, u t du, okay, dt. And what should be the limits of integration? 0 to s. 0 to is it 0 to s or s to infinity? it should be s to infinity, yes, s to infinity, because this will be then e to the minus ut over minus t s to infinity. Okay, so at infinity it's going to 0. At s it will be e to the minus st over minus t, and there will be a minus sign for the second term, so it will cancel out. So you will get e to the minus st over t. Okay, so now we would like to swap the order of integration, right? So change of order of integration. This gives you s to infinity 0 to infinity ft e to the minus ut du dt. So you can put it in brackets. And what is the middle term? It's just the Laplace transform of f at u. So this is s to infinity fu du. Is this clear? Is it okay? Any questions, doubts, comments? How can you? Yes, that's a very good question. We have to be very careful when you are doing swapping limits. Okay, so you are dealing with improper integrals, right? And you remember that by definition, what was this integral? Any improper integral like this, 0 to infinity ft dt, is by definition a limit. Yeah, it's a limit. R goes to infinity, 0 to r ft dt, right? So when you are trying to swap two improper integrals, you have to be very careful that you are allowed to do so. Yes. For example, so this is a particular case of an integral. Is it true that suppose you have a function of two variables s and t, okay? You integrate over t and you take the limit of s tends to 0. Okay? Is it true that this is equal to integral of f limit s tends to 0 f of s t dt? No. In general, no. Okay? So you have to be very careful, and there are conditions on this type of integrand for a function of two variables when you can do that. Okay? So since I have very nice functions, these are of exponential type, these integrals are actually uniformly convergent. Okay? So I'm using a term from functional analysis or topology. I will not explain what is uniformly convergent, but I will just write down a theorem which will guarantee that you can do such change of order of integration. Okay? So be very careful. If f is not of exponential type, in general you cannot do that. Yeah. Again, for example, if you have, we know about differentiation under integral sign. Yes. So suppose that d over ds, take 0 to infinity fst dt, is it equal to 0 to infinity del over del s f of st dt. This is also not true in general. Yes, you cannot just put it inside without checking some conditions. One example is when f of st yeah, f should be differentiable in the s variable, otherwise this will not make sense. But there are also other conditions. Okay, for example, this thing should be integrable. Yeah, in this region. If it is bounded by an integrable function, absolutely bounded by an integrable function, then you can swap limits. Okay, this is something called dominated convergence theorem. Okay, dominated convergence theorem. So if you want to explore these conditions, you will be forced to go deeper into function theory. Okay, there is no way out. So you have to learn what are the convergence criteria, when can you swap the limits. Okay, so this is also swapping limits, by the way. This derivative is a limit by definition, right? So you are also swapping again limits. Yes. So I encourage you to explore these conditions. Okay, I will ask in next class what are the right conditions and what is uniform convergence. No, I'm just kidding. But yeah, in your free time, please explore and try to understand what are the right conditions for swapping of limits, especially for improper integrals. When you have definite integrals, then it's not a problem because things are finite. But whenever you have infinities, you have to be very careful in doing these things, these operations. Yes? If f is, you mean this thing? Yeah. If f is just continuous, are you sure? No. I'll give you an example. So suppose I take this is 0 to infinity sine t sine of yeah, you have to change the variable. So let me just check what was it. Yes. So take sine st by t. Okay. When s equals 1, is it continuous? This function, is it continuous for s positive, for example, at t equals 0? The only problem is at t equals 0, and it will be continuous. Yes. Yes, so it is continuous. If s is positive, t is positive, and you pass to t towards 0, it will be continuous. Yeah. But so this is just actually you can change variables here, and this goes away. Okay. So for example, I just put u equals st. This is what? Du is what? S dt, right? So what will be this? 0 to infinity sine u. Then you have u by s, and dt is du by s. So s goes away, and this is actually a finite integral. What is the value? Pi by 2, exactly. Pi by 2. So in fact, when you're differentiating outside this integral, you are differentiating a constant function, so you should get 0. Okay. Now let's check this right hand side. What will you get? You are differentiating, so you take the partial derivative of sine of st, so you get t cos st by t. So t goes away and you have 0 to infinity cos st dt. Is this integral well defined? No, this is a divergent integral. Okay. So on the one hand you get 0, and on the other hand you have something not defined. So you cannot just swap things without checking the right conditions. So let me write down a theorem. Let me write down a theorem which is a very general theorem, and you can use it in these situations. Say it again. If f is
differentiable.
Yes.
It is integral.
Yeah, so the thing inside the integral should also be integrable. Yes, absolutely integrable. So let me just write down, where is it? Yes. So theorem, please pay attention because this is a little bit technical. So if a function f is continuous and Riemann integrable on any finite interval, a less than equal to t less than equal to b, from 0 to infinity. Okay, and if you define this function hx, which is the integral of ft between the values 0 and x, okay, and hx is bounded as x goes to infinity sorry, there's a more side. If this function is bounded as x goes to infinity, then the integral of 0 to infinity ft dt and 0 to infinity mod of ft dt exists as improper Riemann integral here I put a remark without explanation, as well as Lebesgue integrals. So those of you who are familiar with measure theory, they will understand that Lebesgue integration is another way to define integrals, and it has better properties than the Riemann integrals. Yes. And so these two integrals exist, okay, and if you take a sequence Fn is a sequence of functions that converges pointwise to a function f, and Fn f satisfy the conditions above. Satisfying the condition above means if you define Hnx integral 0 to x mod of Fn t dt, and Hx is 0 to x mod of ft dt, are bounded as x tends to infinity, are, so this is bounded as x goes to infinity, then what? Then the integral, the limit of the integrals Fn x dx, or let me put t 0 to infinity, is equal to the integral of the limit and we have said that the limit is just ft, okay. So this is just 0 to infinity ft dt. So we have seen a criteria where you can swap the limit process and the integration process, okay. So now comes a checking part. Now you have to check that if f is, for example, of exponential type, then it will satisfy these properties, okay. So maybe I will just say so since we were doing this integration of ft by t e to the minus st dt, this was the Laplace transform that we started out with, and we wrote it as an integral 0 to infinity ft over t integral s to infinity exponential minus ut, sorry there is no t here, minus ut du dt. Is it correct? Now, I claim that you can apply this theorem in this situation. How? So, take Fn t to be integral of s to Rn e to the minus ut du, okay, where Rn is a sequence of numbers which go to infinity as n goes to infinity. So Rn goes to infinity as n goes to infinity. Now this is an easy integral, isn't it? You can just write it down. What is it? One over minus t e to the minus ut s to Rn. This is minus 1 over t e to the minus urn minus e to the, sorry? Yeah, sorry, rnt minus st. Is it okay? Any questions? By the way, okay. And then one can show that if you integrate sorry, if you integrate from let me just think. So Fn so what is our condition here? We want that these integrals should be bounded. Okay. So no, I'm choosing the wrong function. So let me postpone it because what's the time? So let me postpone this proof because I'm making some mistake. Yeah, okay. There is some subtlety involved, okay. I don't want to spend too much time on it, but I will prove it later on, okay. What I wrote was, I think, correct, but you have to be careful in how to analyze this, okay. So from theorem, so this part is yet to be proved. This is equal to S 0 to infinity to the minus ut du dt ft. And you put du dt here and du here. This is S to infinity fu du. So actually there are two sequences that one has to be careful about, okay, and I will write it down precisely in the next class, okay. It is as you can see, it is not very straightforward. Okay, you have to be very, very careful. Okay, so let's go ahead. So I did integration. So can we cross check? So for example, I'll give you an example of a computation where this is useful. So compute Laplace transform of sine t over t. Okay, what should it be? This is the integral. First of all, you check that as t tends to 0, this limit exists, right? So we can apply the theorem. And this is s to infinity 1 over the Laplace transform of sine t. So 1 plus u square du. What is this? Tan inverse of u from s to infinity. This is pi by 2 minus tan inverse s, and you can also write it as tan inverse 1 over s. Okay, very good. So suppose I want to compute Laplace transforms of integrals. 7 Laplace transform of integrals. So let Fs be the Laplace transform of Ft. Here, f again is of exponential type. Okay. Then the Laplace transform of the integral 0 to t fu du is what? What is this? F of s over s. Okay. So here again you will have this problem of, sorry? Oh, this is using the inverse trigonometric identity. Okay. So you can check that tan inverse of x plus y, sorry, tan inverse of x plus tan inverse of y is tan inverse of, what is it? X plus y by 1 minus xy. So when you have 1 minus s times 1 over s in the denominator, this will become 0. So okay? So you'll get tan inverse of pi by 2. Sorry, tan inverse of infinity, which is pi by 2. So the identity is pi by 2 equals tan inverse x plus tan inverse 1 by x. Okay? You can check this. It's just a game you have to play with the trigonometric identities. Okay, so let's try to prove this theorem. So, one comment here. You have seen that when you divide by t on the left, you get an integral on the right. Here you are integrating on the left and you are getting a division on the right. Okay? Okay, so L of integral of 0 to infinity, integral of 0 to t f u du e to the minus st dt. What to do? Sorry? Rename the
Integral 0 to t f of u, let's call it as the function of t
okay.
over the difference to differentiation.
Very good, yes. So let's call this gt. Okay. So gt is integrals of 0 to t f u du. What is g prime t? It's just f of t, right? Okay. What is g0? It's just 0, yes? This is 0. So now we use the formula for the derivative on g. So the Laplace transform of the derivative g prime t is what? S of the Laplace transform of gt minus g of 0. What is g of 0? 0. Okay. So this implies Laplace transform of g of t is the Laplace transform of g prime of t by s. But what is this? This is just f of t. F of t by s. This is fs by s. Okay? Good. Very good. So now let me introduce this function. These are functions called special functions. There are many. So one of them is the sine integral that I was talking about yesterday. This is 0 to t sine u over u du. So can we compute the Laplace transform of this? This proof was clear for everyone? Yeah? So let's try to compute the Laplace transform of the sine integral. What can we do? We use our properties that we have proved. Yes? So first of all, you have sine u, you want to divide it by u, and then you want to integrate. So there are three processes. Yes? Choose a function. This is sine u. You know the Laplace transform of sine u. We have proved what will be the Laplace transform when you divide by u. Yes? And then we have proved what it will be when we want to integrate. So we use both the properties. So this is Laplace transform of integral of 0 to t. Let's call it gt. Gu du. Okay, where gu is sine u over u. And suppose that we know the Laplace transform of sine u over u, then what is this by the previous theorem? This is the Laplace transform of g s over s. Do you agree? Now what is the Laplace transform of g? We use again the property of division by t. When you divide by t, you have to integrate, right? Okay. So this is integral What was the limit of integration? S to infinity. You have a 1 by s outside. This is the Laplace transform of sine of s, sine of u du. Okay? Is this clear for everyone? Please raise your hands if you have any doubts or questions. It's okay? So, first time I am using the property of the integral with which I get the division by s. When you integrate on the left, you divide by s on the right. And when you divide by u or t on the left, don't get confused by u, t, x, s. Okay, these are just nomenclatures. I can put anything anywhere. As convention, usually we put t on the left, s on the right. Okay, so if you are getting confused with u well, I also used u for the integral on the right, but it doesn't matter. Okay, you can use anything you like. So let me not use u here. Let me use w. This is a integration parameter. Okay. So what is the Laplace transform of sine? 1 by s square plus 1. Sorry, w square plus 1 dw. Right? And what do you get when you integrate from 0 to infinity? 1 by s tan inverse 1 by s. Okay? So we have computed the Laplace transform of the sine integral. Is it clear? The steps are clear? Okay. Now, let me introduce the Heaviside step function. So this is also a special function. Heaviside step function, or this is also called the unit step function. Okay, this is named after a mathematician, Oliver Heaviside, who basically pioneered the use of Laplace transforms to solve differential equations. Okay. So the Heaviside step function, what is it? So for a greater than 0, you can write u of t minus a. What is it? 1 if t greater than a and 0 if t less than a. Okay? So this is a discontinuous function or piecewise continuous. Okay? It has a discontinuity at at a, but it's a finite, it's a jump discontinuity. Okay? Very good. So we want to compute the Laplace transform of u of t minus a. What is it? Let me write down the formula. 0 to infinity u of t minus a e to the minus st dt, which is the easiest thing to do is to break up the integral into 0 to a and a to infinity. What will it be in 0 to a? 0. So you don't get anything. The only contribution comes from the part a to infinity. a to infinity e to the minus st dt. So this is e to the minus st over minus s a to infinity. And what is it? as over s. Okay? So this is easy. Now let me introduce another special function. This is called the Dirac delta function, or what is it called? Unit impulse function. Okay, what is it? So delta a at t is, what is it? 1 by? Okay, yes. So you want to use the limit of functions, yes? Okay. So let me write epsilon. Okay, this is 1 by epsilon for a to a plus epsilon, or you can also take a minus a to a plus a, that's better. A minus epsilon to a plus epsilon, a minus epsilon by 2 by 2. Okay, so this is 0 outside, so elsewhere. Okay, so what does the graph look like? So this is a, this is a minus epsilon by 2, so epsilon is positive. This is a plus epsilon by 2, and this is some constant function 1 over epsilon in this region and 0 outside. So it's just this part. Okay, so this is 1 over epsilon. Okay, what I would like to do is to take a limit as epsilon goes to 0. Okay, so when epsilon goes to 0, this rectangle becomes thinner and thinner, but also higher and higher. Okay, so in fact the limit as epsilon goes to 0 will not exist, it will be infinite, it will diverge. Okay, so limit epsilon goes to 0 delta a epsilon t does not exist. As a function, even though we call it a Dirac delta function or a unit impulse function, it is not a function. Okay, nevertheless it is very useful in solving differential equations, and you will see why. What is the Laplace transform of this guy? Can we compute the Laplace transform of delta a epsilon t? What is it?
Let's rewrite in terms of units.
In terms of u.
Units.
Okay. What will it be?
1 by epsilon.
1 by epsilon.
A plus epsilon by 2.
U t minus a epsilon by 2 minus, yeah, a plus epsilon by 2. This is a plus epsilon by 2 u of t minus a minus epsilon by 2 anything else? Is there a 2? Say it again. Yes.
But our Dirac delta function, the domain is a minus epsilon by 2 a plus epsilon.
Okay. Sure, sure. Okay, so keep this in mind, okay, for later. Okay. So you are saying that you just use the formula, yeah? 0 to infinity delta A epsilon t e to the minus st dt. So this only gives you a contribution in this interval, and all other things become 0. Yeah. So you get a minus epsilon by 2 to a plus epsilon by 2, 1 by epsilon e to the minus st dt. And what is this? E to the minus st over minus s, a minus epsilon by 2 to a plus epsilon by 2. So you have e minus s a plus epsilon by 2 minus s a minus epsilon by 2. I'm sorry, s epsilon by 2. Okay, divided by minus epsilon s. Is this correct? Is correct? Okay, so actually you can take e to the minus sa outside. And you're left with e to the minus epsilon by 2 minus e to the plus epsilon by 2 s by s epsilon, and there is a minus sign. What is this limit as epsilon tends to 0? Can you prove it? 1 or minus 1? 1? Yeah, this will be minus 1 actually. So this is an exercise. Prove that the limit epsilon tends to 0 e to the minus epsilon by 2 minus e to the plus epsilon s epsilon by 2 by epsilon s is minus 1. So in the end you have e to the minus as. So if you're taking the limit here, so you have limits everywhere, yes. So limit you get e to the minus as. Okay. Is there any comment to any similarity that you find with the unit Heaviside functions Laplace transform? That is e to the minus as, and this is e to the minus as over s. right? So we can write so the Laplace transform of the Heaviside function u t minus a is e to the minus as by s, which is the Laplace transform of limit of the Laplace transforms delta a epsilon t over s, right? So it gives you some idea that in some sense the derivative of the Heaviside function is the Dirac delta function. Okay, they are not. So the delta function is not a function, but one can define a concept of a derivative under which, because the Laplace transform of this is s times the Laplace transform of this, okay, and this happens when you have derivatives, right? When you derive on the left, you get multiplication on the right. I mean, I'm talking in vague terms, but you can make this idea precise, and in fact, you can just put it as a remark for you to explore. The Dirac delta function is called the weak derivative of the Heaviside step function. Okay? If you want, you can explore it later. So you have to learn about theory of distributions. Okay, so one property, important property of the Dirac delta function is that integral of 0 to infinity f t delta t minus a, okay, sorry, I put it like this, delta a t dt is equal to, what is it? The delta function at a is f of a. This is a very important property, and for example, physicists don't worry about taking interchanging of limits and integrations. They consider, for all practical purposes, they consider the Dirac delta function as a function, okay, and mathematicians will try to make it more precise and talk about the Dirac delta function as a distribution, okay, and it will still satisfy all these properties. Okay, so let me maybe write down what I'm calling it. This leads to the theory of distributions. So this is for you to explore later, okay. Here you can define, for example, derivatives of non-differentiable functions also under some conditions. So they are called the weak derivatives. Okay, so we have only 5 minutes left. I wanted to talk about initial and final value theorems, but I don't think I will have time for it. Just one quick theorem. So we want to know what is the limiting behavior of functions. Okay, we want to know, for example, in engineering processes, the Fs gives you some output, and you want to know what will be the large time limit of this output. What will it be after a long time? And so we want to know the limiting behavior of the Laplace transform and also of the input. So the first thing is limit of s tends to infinity, f of s is 0. Okay, it goes to 0 when ft is of exponential order, is of exponential type. Again, here you have a sort of swapping proof. You write limit s tends to infinity of integral 0 to infinity ft e to the minus st dt. When ft is of exponential type, you can swap the limit and the integration. So you will get 0 to infinity ft limit s tends to 0 infinity e to the minus st dt. What is this? For t positive, what is this limit? It's just 0, right? So you get 0. This is a one-line proof, but of course, this theorem is that I wrote down about the swapping of integrations and the sequence of functions. This is behind. Okay, you can justify this swapping using that theorem. Okay. Like I said, I also want you to learn about all these technicalities about uniform convergence and when you can swap sequences and limits and integrations. Okay, changing of two limits. In the end, it's just a swap of two limiting processes. Yes, and it will be very good if you can learn what are the right conditions. In the end, you might have to learn about measure theory and Lebesgue integration. Okay, so the theorem I wrote down, it's a form of the dominated convergence theorem. Okay, and Lebesgue integration is based upon this crucial theorem. Okay, very good. So let me stop.